Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson, and Fred and I were just talking about how, especially when it comes to reliability engineering, data analysis doesn't mean a lot unless you pair it with a failure mechanism or something which explains physically what generates this data.
Well, before I get into that, one of the things you mentioned, Chris, was that and I think the quote was, if I heard it right, was you'd received a tranche of data, right? And I was like, going back to my SAT prep days for the vocabulary stuff, I think you meant pile of data would be the way I did it.
Yeah.
Is that equivalent or similar concept, but you're using like an actual word that means that?
Yeah, so if you mean an incoherent set of numbers that were loosely connected together that I had to spend a good number of hours trying to piece together what they actually meant, then yes,
okay,
I had a tranche of data.
Right. Now, but when you were talking about, you received this data, you did some analysis to see what it meant, and it was time to failure data, and it had some unique properties to it and stuff, not a lot of failures and so on. And it indicated a particular, phenomena that was likely to happen. We've all heard those stories about the data. If you got a beta on a Weibull plot that's less than 1, it means usually it's this kind of stuff. If it's greater than 1, it usually means it's a wear out and so on. But all that aside is that if any data analysis is not consistent with what's really going on, it's not very compelling. And just the Weibull plot oftentimes is just not compelling. It doesn't tell you the story of what's going on. You can do great, beautiful data analysis and plot it in 3D color and all the other beautiful things. But if it doesn't have a story with it, what makes me think of that is that I was just plotting, there's escalators, and I've used this experience a number of different times, but I was just plotting failure events for a particular escalator in their system over time. And it's a very simple plot. And there was this long period in the middle of the year where no failures occurred. He says, "Oh, we must have got it right." And I says, "No, you took the transmission out and it took you 6 months to fix it." So it wasn't running during that period of time. And then there was other artifacts in it where they had 3 service calls all on the same day. And then like 4 weeks later, there's 3 service calls all on the same day. And then I said, so I went and talked to the technician that went to the 3rd call. And he said, well, I'd been here twice earlier today and there's got to be something wrong because I'm back again. So let me go figure out what that is. And I said, why didn't you fix it the first time? And that led to a whole different discussion.
Right.
But if I just showed him a set of dots over time, over the year, and without that backing of a little bit of evidence of what's going on, whether it's behavioral or whether it's physical, it was just a meaningless plot. So I've run into that over and over again where brilliant data analysis is brilliant. There's no doubt about it, yet it's not enough.
Right, and it needs to tell a story. So, I mean, we'll touch on the example I use, but essentially, the people I was working for, they were expecting, with certain justification, that the failure phenomenon I was investigating could be traced back to manufacturing defects and issues.
Well, this must be a mechanical system because I usually get I usually get the pushback that must be a software problem.
Right. There's no way software could have been involved in this thing. I just got the data points and said, okay, I'll see what I can find, and it was a challenging data set to interrogate just for various reasons. But once we got through it, through the trouble of finding the right approach, it was pretty clear. The hazard rate or failure rate was constant, which means that a brand new component was just as likely to fail in the next hour as a 100-year-old component, hypothetically.
Yeah.
And that usually means that this thing is failing due to randomly occurring external critical stresses. So think about a house and a tornado. It doesn't matter how old or young a house is, an F5 tornado is going to destroy that house. So the failure rate due to tornadoes is relatively constant with respect to the age of the house. Same with vehicle crashes, because most vehicle crashes or vehicle accidents come down to human error. And as a rule, human error, there's no correlation between human error or the rate of human error and the age of the vehicle. So accidents like that tend to have a constant hazard rate.
Although there is some evidence that 16-year-olds in a $200,000 sports car tend to have a higher failure rate.
I know, but there's also, I agree with that, but that $200,000 sports car, which I'm presuming is brand new, so it's quite young, you'll have some more seasoned drivers owning those vehicles as well. So,
Oh no, I'm just being facetious there. I don't have any evidence one way or the other, but yeah, the and I've run into it with there's this one group that it was years and years ago. They made a small little product. I think it was part of a medical system of some sort, but it was a disposable part. So they didn't think reliability had anything to do with them whatsoever. But if the packaging was broken, or if the threads weren't formed right, it didn't mate with where it's supposed to, the people using these things said, that's a failure, and they wanted their money back. So they got these warranty claims essentially. But the data they were using was, they're not serial numbered. They're disposable, and we don't really track which one we made when to relate it to when we get it back. Now they could. It wasn't very difficult for them to do it, but they didn't do that. They didn't see the point. And so they would ship 10,000 units in January, and they might get, 200 back at warranty calls that month from previous makes, shipments, not in January. But they would divide the number of failures they got by how many they shipped that month. And I'm like, there's something fundamentally wrong with the math here.
Yeah.
But that was the metric they were using, and they were trying to figure out, why is it going up and down? It says, well, it kind of correlates to your production. You made 10,000 this month, you made 20,000 that month. And of course the failure rate's lower because you had a smaller population. But that mechanism they never had enough good data to figure out what was going on with their product. Why were these different mechanisms occurring, or what even to look for? It was just so clouded it didn't happen. But most of the time we deal with people that and I've run into reliability engineers that they were like, just show me the data. That's all I want. I will crank it out. I'll give you a Weibull plot. I could mail it to you. We could put it on a poster board. That's all I want to do. And then they were frustrated because nobody uses it to make a difference. It's this one guy down in Houston that was making laptops, and I said, you do halt testing. Why do you see the same failures in the field? That halt testing's for the birds, that overstresses it. I never look at those reports. And the reports were detailing the failure mechanisms that they could have designed out, but they didn't. He just ignored the data in that case. So there's examples all over the map, but there's this point where it's got to tell the whole story, and it's got to be, similar to what we were talking about the last time. Doing that with the data and the underlying story, the failure mechanisms and how they manifest to create that data, is a complete picture, or a more complete picture. But then you still have people that are going to ignore it anyway. And that's back to influence and how you present stuff. But the idea of just saying, there's a Weibull plot, that must be a wear out mechanism. And without understanding what the failure mechanism is, you're not helpful. And I think that's where I'm going with this one.
Well, we're talking about two bunches of people. One, where people are going to ignore everything no matter what you do. Right. And just put them to one side. They need to sort out their priorities, is one way to think about it. They need to be put on a cruise ship and send that cruise ship in a straight line, and tell that cruise ship not to turn and deviate until it runs out of fuel, and then see what happens. You can't do too much about people who just refuse to change. Yeah, that's the first thing. But there's another bunch of people who aren't full-time reliability engineers, and they're not idiots. but they also haven't spent the years immersed in this sort of stuff like you, me, and lots of other people have,
Mm-hmm.
and just where it's not intuitive, and that's okay. It doesn't mean they're idiots. Far from it. It's actually really challenging to be across reliability engineering. The same way it's be challenging for anyone to be a welder. Really good welders are worth their weight in gold, so to speak. The best welders in the world, they spend all their time welding and maintaining those skills. It's just like anything else.
Right.
A part-time welder is not going to be nearly as good as a full-time welder. That's just a fact.
Yep.
But the people I'm talking about are not the group of people. One, the people who are not going to change no matter what you do. You can't help them. Then there's a group of people, number two, who aren't reliability engineers, but they have made their own conclusions that are rational from their perspectives and based on their experiences regarding reliability. In this example, the team I was doing this analysis for, they essentially said, yeah, but when we, and I found this out after I did the data analysis, when we looked at these failures, the mechanical component involved it was bent. It underwent plastic deformation. And their line of thinking was, so the part wasn't strong enough, and so the manufacturer didn't manufacture strong enough parts, or a defect led to these parts not being strong enough to withstand certain stresses.
Well, are they examining this requirement? I mean, there's probably some rigidity or yield strength requirement for this metal, like on a tensile strength or a pull test or a bend test or some other phenomena that this grade of material should have this set of characteristics. I mean, did they even explore that, or do they just go, "Oh, that's what it must be"?
It was. To be fair, it's pretty early on in the exploration process, and the answer was no. But I wouldn't condemn them for that, because it was just, here is a problem. Let's start looking at it, including the data analysis.
Okay, but they had a hypothesis of what they expected to see. That's a good way. Fine. That's a good way to do it.
A hypothesis.
Yeah.
Yeah, that's fair enough. And you know what? It's actually feasible for manufacturing defects, especially heat treating, for example, to lead to a certain fraction of components not being as strong as the other components, and it is possible. But I said to them, look, the data suggests, well, first of all, plastic deformation usually happens from one single, I think you use the term, blunt force trauma event.
Yeah.
It doesn't usually, you don't usually accumulate plastic deformation. Not always the case. Creep deformation is a different one. But this sort of scenario, without going into what this component was used for, creep is not on the table. So what they were observing was classic blunt force trauma events, where one event involved this large amount of force being imparted to this component, and it just bent.
Yep.
So I said this constant hazard rate thing, which we're sort of finding in the results, which doesn't suggest
well, it's not corrosion, right? It's not a corrosion. It's not a creep fracture or a crack that's propagating through, or crystallization of the materials, or any of these other phenomena. I agree with you. It's an indication, and right. I think the best part though is when they said, "Oh yeah, we were bending these things." Like,
right,
oh, okay.
But that is a classic blunt force trauma event, and I said that's entirely consistent with what the conclusions of the data analysis are saying. So they had to learn that, rightly or wrongly, they had these preconceived ideas that, well, some of them are bending, so clearly they're weaker than the rest. But no. The statistics are showing that on average, your systems are experiencing this blunt force trauma event every such and such usage.
Mm-hmm.
And if it was simply a subset of your entire systems having defects which led to reduced strength, then the statistics would show a very, very different picture, because essentially once these defective components were removed from the population's apparent reliability would increase, and you'd see that. You and I have done plenty of these analyses where that's very obvious when that happens, and so that's not happening. And so they had to be convinced, and I think I got there, that what they're observing with their own eyes is actually consistent with what the data was saying. And the reason that's very important, obviously, to get this one right is because, as opposed to them pursuing a manufacturer and saying, hey, your products are defective, and when the actual problem is something else, you are only ever going to end up with continuing substandard products because the defects aren't an issue. You're going to alienate your supplier base and waste lots of time and lots of money before you ever come around to understand what the real problem is, which is something else.
Yeah.
And that's a waste of time you need to avoid.
Yeah, and it puts them in the right path to do the failure mechanism analysis. What caused this bend? And I think there is, let's interrogate it, or interrogate is probably not the right word. Let's talk to the users and see what let's put a camera on them, or, a shock sensor or something like that, and see what's going on, or how is this product being used? And there's all kinds of ways to go with that, but the data help them, along with the story of this is a classic, consistent with this failure mechanisms, classic fit with this data set, the way it's analyzed, what we're seeing. But if you just gave them this a constant hazard rate, they could still derive whatever conclusion they want. It doesn't, unless they're well versed with this nature of these failure mechanisms, the nature of the data sets, all this stuff. That's where I think a lot of us as reliability engineers, some of it's through experiment, some of it's through experience, some of it is us thinking through how does a failure mechanism manifest itself? What is the details of that? Now, we all don't need to be in the lab doing material science, but it sure helps to have a fundamental understanding of the different types of corrosions. When you look at one time I was working with a client, and they were making a little portable reading device, sort of like a Kindle or an iPad, just a tablet type thing. And they showed me the circuit board they were planning on putting into it, and it had a right angle cutout. So think of it as a rectangle with the lower right quadrant cut out, because I think that's where the battery was going, or some other device. But it was just a right angle cut and a sharp corner. And right off that corner, right in line with one of the axes of that cut, was their great big monster CPU. And I said, where are you attaching this? How is it contained within the frame? And it was at the far corners. It was just kind of held by the chassis of the outside frame. And I'm like, now I'm not a mechanical engineer, but I suspect that this circuit board is going to bend, and this large piece of glass, also called silicon, is going to break. And it was just by a casual observation. And it comes from experience of seeing things like this break with not a lot of motion. And they went, how'd you know that? Because they were dealing with broken CPUs, and they were trying to figure out where in the world did this come from. They were blaming their suppliers and their handling and their manufacturing processes. I bet you if you did a finite element analysis, you're going to see enough deformation right there just from normal handling. Mm-hmm. And it was there. I didn't have any data at all, right? Except experience, but they had the data saying, yeah, we've seen a bunch of these things. Does it align? Does the crack that you're seeing align with this axis? And they went, how'd you know that? It's like, so sometimes you come across as a magician, but it comes from an understanding of the data set and where to go look. And then that helps with the failure analysis process, that helps with the design process, all those things. But over time, then we have to still be able to explain it. Here's how this mechanism behaves and manifests itself. And here's where the data would show it, how it occurs. So if you change this slightly, get rid of that flex point or move the CPU to somewhere else, you'll see it in the data set that you have, and vice versa. Sometimes, like you were describing, as the data set points to types of mechanisms. It's one of those phenomena that we just need to keep in mind, is that, just because I have an average of 14 and a standard deviation of 28 doesn't tell us the whole story.
I think there's two parts of this. I think that relating data with how it breaks or how it fails, it's brutally important for people to buy in to the data. Because if you present them with a chart and they just can't understand how a particular failure mechanism could result in those dots or those lines, they're not going to believe it, rightly or wrongly. They're not. So that's the first part. The second part is that if you can't relate failure phenomenon or phenomena with data analysis outputs, then you're going to be constantly trying to solve problem A by solving problem B. You're going to chase your suppliers for poor quality products when it's actually the design of your design of the system, how you use that component, or anything else. You don't want to waste time and money trying to essentially assign blame or responsibility or the cause of a problem on something that's not causing that problem, because you can fix that problem as much as you want, and you're not going to solve the problem that manifests itself in your system. So there's the two reasons. First one is buy-in, so people can relate the numbers to their understanding of the world around them, which is a very human thing. And the second thing is knowing what to fix.
Yep. Now, I'd say there's a third one, and sometimes the data and our understanding of what we think the mechanism is inconsistent. For example, if you're expecting your data to give you a nice linear regression, right? Nice straight line. And you run the experiments, you collect all this data, and it's a curve, and it doesn't fit. And you want to fit a straight line to it. And I'm prompted because this morning I got an email saying,
life testing.
Yeah, doing accelerated life testing. And what do you know about Arrhenius? And they're like, well, but if the Arrhenius works great, if it's linear, if your materials change properties at different temperatures, and it's not incorporated into that model, Arrhenius is only part of the picture here. We're missing some part of the data. It's basic regression analysis. If the data is curved and you're fitting a straight line to it, you're missing something. And so sometimes the data's analysis challenges our understanding of the mechanism.
And I'm not sure how many people who are listening to this would have heard of ALT, accelerated live testing.
Well, this is a great audience. They all know what this stuff is.
Well, just for the one or two who haven't. Essentially, what we can, for many chemical reactions, we can essentially make them happen faster if we increase the temperature. And there's a good, well-known relationship called the Arrhenius model that describes that. And that's great, which means that you can essentially heat something up and maybe compress 10 years worth of usage into a week, which is fantastic if you're trying to work out how long something that needs to last a long time is going to work. What Fred is talking about is that the Arrhenius model, which essentially creates those straight lines when you increase the temperature with how long it lasts, if your system changes due to the increased heat, sometimes it's as simple as a metal's microscopic structure changing how it's put together, you don't get that straight line. So if you don't see a straight line for accelerated live testing, it means that you don't understand everything you need to understand about your system to do that sort of analysis.
Yeah.
And it means you need to start reading or researching or testing or analyzing.
Yeah, exactly. So I think, I'd say there's three parts to it. Is sometimes the data and the mechanisms support each other and give you a good path, and the two concepts you talked about, Chris, but sometimes it says you might not really understand the mechanism well enough. You need to learn something, or you got really bad noisy data and there's multiple failure mechanisms and all kinds of other problems, which is the subject for a whole nother discussion. When you get that tranche of data and it makes absolutely no sense whatsoever. Right. Or my favorite is the guy shows up with a set of experiments that he's run and all with very few samples and all not coordinated in any way, and says, "Can you make sense of this?" Like, probably not. You're a statistician. You can make sense of this.
I must admit that the data analyses I do, it's quite rare to get something which is completely befuddling.
Oh, this guy was a brilliant experimenter, and he twiddled every knob he could think of in an incoherent way.
All right, okay.
Yeah, no, it was like, no, can't help you.
That's somebody else's data analysis, so you can't be responsible for that.
That's right. That's right. But anyway, so yeah, when you're thinking through your reliability work and you're looking at data, always think about the mechanisms underlying. What's the world trying to tell you? And then are they consistent? Can you put together a good story? It goes a long way to being a whole lot more effective in in doing what we do. So if you got a question on this or an example or something that you'd like to explore, let us know. Head over to accendoreliability.com/go/SOR, and you can find a couple of ways to get in touch with us there. Chris and I and the other hosts of the show are available through LinkedIn and or our About pages. So there's plenty of ways for you to get in touch. So, Chris, I'm itching for a good tranche of data. I just like that word. That's going to be my word of the day here. I was listening to our, thinking back to our last episode, and I said, he used a word I'm not that familiar with. It's like,
I'm glad I'm touching lives in so many ways.
There you go. Yeah, I appreciate that, Chris. So have a great day. Good luck. Have fun with your data sets, and we'll see how it goes.
How can you not? Always a pleasure, Fred.
Cheers. Talk to you later. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.